G'day viewers. In this segment we'll talk about routing when there are multiple parties in the network. So this formulation for routing is very much like the internet in which we work. The network is comprised of multiple parties altogether, and in the internet here they're the ISPs. You can see 3 ISPs here. And the complication is that each of these parties might have its own goals, its own idea about what would be a good route. Yet somehow they all need to work together to be able to get traffic, from a source to a particular destination across the network. Okay, so first of all, let's just drill down on the overall formulation a little bit by looking at the structure of the internet to give us a better idea of what we're talking about. So here's a picture of the internet architecture, and you can see that there are a series of different networks here that are shown. There are 1, 2, 3, 4, 5, 6 different networks that are connected here. The networks act as they source and sync traffic. They have different prefixes here. We talked about prefixes being blocks of IP addresses. They're everywhere here. These are all the sources and destinations on the networks. Now there are different kinds of networks. ISP networks, host customers here, CDN networks provide content which is often delivered to the customers at ISPs. There are maybe other kinds of networks, enterprise networks and so forth. All of these different networks are richly interconnected with one another in all sorts of different ways. They might be connected directly, but it's a common strategy that many different networks will actually connect together. They will connect to what's called an IXP. IXP stands for Internet Exchange Point. And an IXP is really a meeting place where many different networks can come together and exchange traffic. Now, our routing problem is that somehow, even though these are all different networks run by different people, and hence they have different ideas of what routes they would like to choose, we want to be able to find routes from a source, let's say the CDN here is sending traffic, somehow to reach a particular destination, such as a customer here within this ISP. Well, we'll get to how exactly we do that in a moment. What I want to talk about first of all are just the issues which are introduced by this internet-wide view of routing across multiple parties. Because really, these multiple parties bring in 2 different problems that go beyond what we've seen in routing in individual networks. The first one is just of scale. We now have a very large network because we're gluing all of the different networks we could think of together to form the internet. So we're going to need to use techniques to improve the scaling of the network. We've already seen things like IP prefixes and how they provide hierarchy, and we'll see other kinds of the scaling techniques that will be used, such as prefix aggregation. I guess we talked about that, but we'll also see the use of how we can use these parties also for a bit of scaling that's going to help. The other thing that I want to talk about in more detail, because this is really what's unique to the multiple parties, is that we need to incorporate what are called policy decisions. Each different party, I've said before this abstract statement, they might have their own idea about what constitutes a good route. So they might want to choose routes, or at least portions of routes, to suit their own needs. The way they choose it is described according to a policy. So I said yikes here because, what's going to happen to the overall route when different people are trying to choose different portions of it? Will it even work? That's exactly the issue. In fact, having different parties in the network with different preferences can lead to some strange effects. So let's look at the kinds of things that can and do happen in the internet today. So here's a simple model network. We have 2 ISPs, ISP A on the left and ISP B on the right. Now, the policy for each of these ISPs is that they want to choose the shortest path within their own network. Why? Well, if they carry the traffic the shorter distance, it'll probably be cheaper, and that way it'll be more cost effective to run the network. Okay, that seems like a pretty reasonable policy. And actually, you might think that if everyone chooses short routes, everything would all be fine. But let's see and that we would get short routes overall. That's not quite what's going to happen. Let's look at what happens. Let's consider, amongst all of the different prefixes we have here, just the path that gets chosen between traffic going from A2 to B1. So here is A2. We start inside ISP A. ISP A gets to control how traffic goes through its network. So from here, we want to send it along the shortest path to reach B2. Well, we could go via any of these different points, these links which connect to B ISP-B to reach prefix B1. This is where we're trying to reach, not B2. So which of these am I going to choose? Well, I'm going to choose the one that's closest to wherever I am because that will be the shortest path in the network. Now I've drawn this figure so I can tell you that this one is the shortest path. So then we'll go over this segment here, out the network, we'll land in ISP-B here, and we'll take the most direct path to B1 here. Okay, it's a little bit of a roundabout path as you can see. Well, what about the path from B1 to A2? Okay, well, I start in B1, I'm going to go back, but I similarly want to go to ISP-A to reach prefix A2. I could use any of these three exit points, which I'm drawing. The closest one is this top one here. So I will go there, and then across the link. Then within ISP-A, I'll go directly to prefix A2. So you can see here the result of the best paths that would be found according to these two policies, if we could somehow come up with a mechanism to find them. And I've just cleaned up this diagram to draw them, and I'd like to make a few points about these paths because they're not quite what you might expect. If we had done one overall routing formulation and called this one big happy network, we would have found the shortest path between these 2 points. Actually, both of the shortest paths between both of the paths which is selected according to these policies from A2 to B1 and back, neither of them are the shortest path. The shortest path here is the one that's shown in the pink. I'm tracing over it, and we took a different path in one direction that was longer and a different path in the other direction which was also longer than the shortest path. Not only that, but the two paths are different in different directions, so they're asymmetric. So you can see that policy routing, in fact these effects are common in the internet, policy routing often leads to asymmetric paths where it's different going from A to B than B to A, and often paths which are not quite shortest. And these effects are really consequences of the independent goals and decisions which have been made by the parties, rather than simply the effect of hierarchy hiding a bit of information causing us to take longer paths. We've seen that effect too. Well, so this is what we're up against. What I'm going to do now is talk just a little bit about policies, and then we'll have fulfilled our goal of just understanding the formulation for routing with multiple parties and what policies are. And later in the next segment, we'll move on to BGP, the protocol which finds policy routes in the internet today. So policies, the idea with policies is that they'll capture the goals of the different parties. Now, policy is this general word, and that's because it's abstract, because policies could actually be anything. Here's an example of a real policy. The Internet 2 is a research and education network in the United States that's used to connect universities. One of its policies is that it will only carry non-commercial traffic. So it will carry traffic between educational institutions, so UW to MIT and back, but it won't carry traffic from those educational institutions to commercial networks, so that we could all serve Google, for instance. Why? Well, that's just its acceptable use policy, because that's what the network is for, and that's a condition of funding the network. So the routes will be computed to comply with this. That's one policy. In fact, we don't know for all of the commercial networks exactly what their policies are, because these are proprietary. They can depend on the two different parties that are connecting, can have all sorts of different policy. What we're going to do instead is talk about two common policies. I'm going to talk about the policy of transit. ISPs give transit service to their customers. That's one kind of common example of a policy that's often held up. And we'll talk about a different kind of policy called a peering service, where an ISP provides a peering kind of service. Two ISPs often provide a peering service to one another under some situation. So let's look at those two policies. Well, here's this transit service. So the idea of transit service is that one party in this deal, that's the customer who's going to pay for this, is going to get what's called transit service from another party, the ISP. So transit service is what you get when you connect to your ISP. You're paying it for transit service. And the idea of transit service, the policy, is that the ISP party, I'm going to refer to them as just the ISP and the customer, will accept traffic from the customer and make sure that traffic can be delivered to anywhere else in the network. So you're a customer here, you can hand packets to your ISP and destined for wherever, and your ISP will somehow send them to the rest of the internet, and where they will reach customers who are outside that ISP. Similarly, your ISP will accept traffic from the rest of the internet and deliver it to you. So some traffic could come from here, and the ISP will accept this traffic because it's for you and make sure that it gets to you. And you, the customer, generally pay for this privilege. When we connect to the internet, pricing often depends on the amount of bandwidth we have, the size of our DSL link, how rapidly it can send information. But often what we're really paying for, as well as the size, is connectivity to the rest of the internet, the ability to send traffic and receive traffic from all of the other destinations that are out there. And the transit policy is providing us that. But there are other kinds of policies too. And here's our peering policy. In this policy, we have two parties. I have ISP A on the left and ISP B on the right. These parties are both going to give one another, they're going to use a policy which gives peer service to each other. Now, in peer service, each ISP accepts traffic from the other ISP only when it's for the customers, to and from their customers. So I have the two customers down here, and you can see we can send from one customer to the other across this link and back. And similarly for the customers up here, we could do the same. Okay, that's great. You might wonder what are precluded by that. Well, actually, why is this not transit service? Well, here's what ISPs don't do. ISPs do not carry traffic to the rest of the internet for each other. So, in fact, customer A1 can't send via this link to reach some other place on the internet. Not allowed. I'm going to cross that off. Not allowed. We don't do that. Why? Because that's not part of the peer policy. So it will allow, the ISPs will allow these routes just between their customers, but not further out. And as a consequence of this, both ISPs are sort of doing one another a favor, because by doing this, they then don't have to send traffic via a transit provider and pay for it. And usually as part of peer service, we say that the ISPs don't pay one another because they're both providing value for each other. So these are the two policies that we've seen. And in the next segment, we'll look at a mechanism called BGP, a protocol, which finds these kinds of routes in the internet today.